Swayam Prabha. Digital India. Educated India.
So, if you look into this particular slide, left hand side you see a particular plot which tells you the carbon budget which we have, CO2 budget which we say, we have currently to keep the global warming below 1.5 degrees of pre-industrial temperature. Okay, so basically you will have to avoid that 1.5 degrees. So, if you have to avoid 1.5 degree rise compared to what we had pre-industrial time, you see we have a budget of 250 billion tons of carbon dioxide, and currently the amount of CO2 which is being emitted worldwide is roughly 41 billion tons of carbon dioxide every year. Okay, so if you do a small math, you see that in another 5 to 6 years we would be able to basically we will be emitting roughly 250 billion tons of carbon dioxide into the atmosphere in business as usual scenario. If we don't do any capture and if we keep emitting the CO2, we will be ultimately emitting minimum 250 billion tons of carbon dioxide into the atmosphere. Why I am saying minimum? Because even today we have not peaked. Now, this is what I was trying to basically talk about in this particular slide. So, when you see some of the literature which is little dated, for example to 2018 and around this time, it was suggested that there is going to be a peak of CO2 emissions sometime in 2020. Okay, those days 2018-17 people used to do this kind of predictions, and they used to say that we are already doing huge amount of CO2 capture and utilization and sequestration projects. So, we believe that by 2020 we will be able to peak, and after that it will go down. But today, as you see, 2024 we have not peaked yet. The rate at which CO2 emission is increasing year by year is roughly 1% worldwide, and if you talk about India, it is increasing roughly 5% every year. So, every year there is a rise of 1% additional CO2 compared to previous year worldwide, and every year there is a rise of roughly 5% additional CO2 compared to previous year if you talk about India specific data. So, if you look into this, now there is a new prediction which says that we are going to peak somewhere around 2030. Okay. Now, these predictions typically comes based on how much investment has gone into CO2 capture, utilization and sequestration kind of projects, and expected that based on the carbon credits people may earn, based on the tax benefit people may get depending upon which country you are, you can do some kind of a calculation to know what exactly has to be done and how much CO2 emission will be cut over a period of time. If you look into this, if you have to go below 2 degrees, you have to go below 1.5 degrees. If you are supposed to be at 2 degrees, these are the significant CO2 emission cut is needed. We will talk about it later, but let's go back to this slide again. So, what we see here is that the 6 year or 5 years duration which we have to emit another 250 billion tons of CO2 into the atmosphere, it basically means this is the bus which we have already missed. We will not be able to contain the 1.5 the temperature, global temperature beyond 1 or below 1.5 degrees of the pre-industrial time. So, if the pre-industrial time, if the temperature was say 25 degrees average, it is assumed that it will become average 26.5 degrees in another 4, 5, 6 years. So, if we would have really wanted to cut it or keep it below 1.5 degrees, most of the technologies which we have already developed must have been implemented right now. It is not working at this moment at this pace. So, this is gone. Let us now look into this 2 degrees scenario. Now, for the 2 degrees scenario, that is you have to avoid the 2 degrees rise compared to pre-industrial temperature. The carbon dioxide budget which you have is roughly 1150 billion tons. Now, this is a number, does not mean that this is exact number. This also tells you there is a 50% chance that if you emit more than 1150 billion tons of CO2 into the atmosphere, there is a 50% chance that the global warming temperature will be beyond 2 degrees of what it was there pre-industrial time. So, let us assume 50% chance is what we are now talking about. Here also we gave that same number. So, 1150 billion tons of CO2 is what you can maximum emit And this basically brings to this point, very important point, this is your lifetime target. It's not a target for 2050 or 2070 or 2100. If you are any time in next 100, 200, 300, 500 years goes beyond this number, the temperature will go beyond 2 degrees centigrade. So basically it means the lifetime target we have is 1150. So if I have to now contain the temperature below 2 degrees, obviously we can't consume our lifetime target by 2070 or something. So we need to basically understand that somehow we have to emit only roughly 50% or 60% of this till whatever time we claim that we would like to become net zero. Okay, for example, US claims that they would like to become net zero by 2050. China says that we will become net zero by 2060, and India has committed that by 2070 it would become net zero. So it basically means that US has to take all those measures so that by 2050 or before that they should not be emitting more than 500 billion tons of CO2 every year. So it basically means currently what we are emitting worldwide 40 billion tons. It basically means that in today 2025 to 2050 we have 25 years. If we keep emitting 40 billion tons, it basically means that we will emit almost 1000 billion tons by 2050. So if we emit 1000 billion tons by 2050, we will be within 2 degrees almost. Okay. So it basically means that we need to cut at least 50% of the CO2 which we are currently emitting. Okay. Instead of 40 billion ton, if we emit only 20 billion ton, next 25 years we will be emitting another 500 billion tons of CO2. So we will remain within that 1150 number what we have. So this is why US wanted to target this by 2050. That if they can somehow emit 50% of what they are emitting today, then they will be able to meet this target and they will be fairly below that 1150 number. That would ensure that they would be, or the global average would be such that the temperature will not go beyond 2 degrees in near future. This is the challenge. 500 base. So 20 billion tons of CO2 cut is the challenge. Now this is the benchmark which we have. If we have to cut down 500 to 700 billion tons of CO2 from today till 2050, what has to be done? Okay, what you will have to do? You will have to break down all those sectors from where there is a CO2 emission. Okay, power sector is the biggest culprit. Most of our electricity comes from burning fossil fuel, either coal or other form of fossil fuel, oil, gas, whatever you talk about. So if you are burning coal, this is the worst, because coal, if you are burning, coal is mostly made up of carbon. So you are burning coal to produce electricity, that's the product, but there is another product in this process, that is the carbon dioxide. Okay, C plus O2 will give us CO2. CO2 is a product. Energy is actually a byproduct which we use. Actual product is CO2. Now what is the challenge? We are saying that we will run a process where we will capture the product and put it back. Now this is a big challenge, big task. So far in human history we have not done anything like that. People typically compare such things with pollution control and all those things. Pollutions are typically byproducts. They are in ppm level. SOx, NOx, all carbon monoxide, particulate matter, all of these which we have somehow handled either below or from the tailpipe of vehicle or from point source, we have only handled the byproduct which are in not even 1%. Today what we are talking about, we are saying that we will capture the product itself, and it's not pure which is available to you. It comes as 10% mixture with remaining 80 to 90% of nitrogen. This makes it even more difficult. So this is the challenge, and this is why it's a very tricky situation what you will do so that you will become net zero. This is why the title was net zero, not CO2 capture. We have to always keep that in mind. The focus is on net zero. It's not about CO2 capture, producing more green energy and all. Focus has to be on net zero. If we are not able to achieve a process which ensure that we are moving towards net zero, it's of no use. Okay. So power sector, though it is easiest to handle the power sector, because in power sector it's very easy. You are currently using fossil fuel. If you move from fossil fuel to renewable sources like solar, wind, there are other geothermal and all other sources are there, including nuclear. So we should be able to move from CO2 emitting fossil fuel based processes to non-CO2 emitting, or I would not say non-CO2 emitting, I will say limited CO2 emitting sources like solar, wind and all. Every process will emit CO2 if you do a proper LCA, but compared to fossil fuel, which actually is mostly carbon and hydrogen, if you are doing the combustion of anything which contains carbon, ultimately you will have to produce CO2. There is no other way out. So this is the easiest to maintain, but how do we control it? If I have to cut down 700 billion tons of CO2 from power, majority of it will move from fossil fuel to renewable. That's how I will be able to cut my CO2 emission. That is roughly 200 billion tons of CO2 we will be able to do by this. Whether we will be able to achieve it or not, that's a different story, but this is what we will have to do. Okay. Now this is the target. How much we are able to achieve, that's a different story. So this the majority of our CO2 cut is going to come from power sector, and that is basically moving from fossil fuel based electricity generation to non-fossil fuel based electricity generation. Okay. Then a significant portion of it is going to come from CCS, or sometimes people call it CCUS, that is carbon dioxide capture, utilization and sequestration. I will talk about it in little detail later. And then the other almost similar amount will come from nuclear. So many of the countries which somehow they will not be able to basically go to renewable, or they will not be able to ramp it up. Challenge is mostly ramping it up. I will talk about that challenge at some point of time in this talk. But there are certain challenges, we need to understand that also. So there are some challenges. So you see here, these three put together will be able to cut down roughly 300 billion tons of CO2 from today till 2050. We know what we have to do. Whether we will be able to achieve that is a different question. Similarly, in the other industries, chemical industries and all, being a chemical engineer, I will only talk about chemical industry, transportation, buildings and other transformation, all kind of things emit lot of CO2. Where the CO2 emission comes from, all this? Transportation easy for you to understand, but what happens in industry and other transformation? See, typically what industry does? Industry basically does produce a material. So when you produce a material, you will emit CO2, because there is no other way to produce a material without using energy. The energy source is only fossil fuel based energy source. So if you are producing even a gram of material, you are going to emit more than a gram of CO2, that's given. So it basically means that there is a contradiction. What contradiction we have? Today we are talking about increasing GDP. Why do we increase GDP, or how do we increase GDP? We have to increase GDP by consuming more. So if you are consuming more, it means you will produce more, and if you are producing more, it basically means you will emit more. So there is a contradiction. If I have to control, or I have to keep growing at the rate at which my GDP is growing, there is no way that you will be able to contain the CO2 emission as of today. How do we do that? You will have to basically convert it into the current way of electricity generation, which is fossil fuel based, has to go from fossil fuel to renewable. Okay. Now in terms of India, I told you that there is roughly 5% rate at which CO2 emission is increasing in India every day. Let's try to break it down little bit further. Why we are increasing at 5% while world is increasing at 1%? Obviously our GDP is growing at roughly 7 to 8%. This is what we are seeing, and we want to keep it growing. We have our target to become this kind, third largest economy, then second largest economy. Ultimately we would like to become the largest economy in the globe and all kind of things. So there are certain targets. Why these targets are there? These targets are there because all these people sitting here who are students today, tomorrow they are looking for jobs. If you will not grow, you will not get jobs. Okay. Those people who are in industry, their kids are studying in very fancy school, paying lakhs of fees. If you are not able to grow in your job, you will not be able to teach your kids to pay lakhs of fees. So you see, this is the requirement. Can we say that we don't want to do all this? So if you do this, you will have to grow the economy, the GDP has to grow. So this is where the contradiction starts. Now one way of doing it is that if my GDP is growing in country like India, if the GDP is growing at 7%, 8%, if I should be able to, if I don't want to touch my economy the way it is going, I need to basically install roughly 7 to 8% the additional energy which we need every year. I should be able to install green energy for that. Okay, so we want to install some 7 to 8% of our total energy requirement through green energy every year. This is the target, and this is what the target was. We had some 500 gigawatt solar and all those targets were there. But unfortunately, even do you want to do it, you do not have that much of supply. Okay, there is a supply constraint. Okay, so we are growing roughly around 4% to 4.5% in terms of green energy installations. Okay. So the reason now there is 5%, 8% is what you want, you are growing, and you are able to implement some 4%. So that gap of 4% actually is ensuring that you still have to pump more coal every day, every year. So last year and the year before last year, the difference is 8% additional coal. Okay. So in 2022, if you have consumed X amount of coal, in 2023 India consumed 1.08 X amount of coal. So even in today's CO2 constrained world, we are forced to consume more coal, because the rate at which we are growing, we will not be able to grow if we actually stop consuming coal. Okay, so this is where that 5% comes from. Let's move on. So what I am trying to tell you, whatever the take home message of these two slides are, 1.5 degrees gone. 2 degrees is what we are targeting now. Now if you have to target 2 degrees, one of the two options which we see in this particular slide is, one, move from fossil fuel based energy sources to green energy sources. That is going to reduce your CO2 footprint, and whatever CO2 which you are producing because of all the material, electricity and all those things, you will have to capture that CO2, utilize it or sequester it. Now this is the two steps which we have to understand. What are the challenge in these two steps? So the first is it easy to go from renewable or non-renewable or fossil fuel based energy economy to renewable or green energy? So let's look at the data what India has shown so far. So this data over here you see is from 1985 to 2022, and this talks about the energy mix, the renewable energy mix of Indian economy. Okay. And this renewable energy is basically coming from hydropower. We have done a significant amount of hydropower installation in last 25-30 years. Solar, wind, biomass, waste, geothermal, wave, tidal, all of these put together, actually we are going down. With so much of talk about biomass, hydrothermal and all, the rate at which our population grew and the rate at which we actually grew between 1985 to 2000, without bothering or looking for cheap energy sources, we have actually installed huge amount of fossil fuel based power plants, and this is why the total energy mix you see, we started at 25% and we went down to 2005%. There are other challenges over here. For example, we had very good practice in villages to go for this, we used to call gobar gas, okay, biogas and all those things. Those things were being used because natural gas or piped natural gas or LPG, whatever we know today, was not easily available to us. It was very expensive. Other countries were not exporting and we were in really big soup. We didn't know how to, so this we were forced to do it. It was more sustainable, but then those days it was thought, oh, since we are not able to afford, this is why we are doing it. As soon as we started affording it, we started discarding all of those sustainable practices. So entire village, if once the cylinders were available, we were saying, oh, we will give you free. Not one, not two, we will give you 6 free, 8 free, 12 free. So these all went on, and ultimately the entire biogas, gobar gas, everything were junked, everything stopped working. I mean, the things which were working, we started claiming, oh, it does not work anymore, there is a corrosion problem, there is this problem, there is that problem, and then we said, okay, fine, we will not do it. So now instead of getting your energy at least for cooking, which used to come from renewable sources, now you are getting it from fossil fuel, because you now have no more natural gas, you have naphtha, you crack it and produce whatever you want, and then you basically start using it. Was it sustainable? It was business oriented, it helped grow the GDP, but it was not sustainable. Okay. So this is the reason why it went down, and then somewhere around 2005 we realized, oh, we are going in the wrong trajectory, we will have to correct it. So we started correcting it. For some time it took us to correct it, and now we are actually improving. Okay. We hope this trajectory will keep going up and up, and we will become sometime around 1985 data, we will have something 2035. So it basically means from 1985 to 2035 we have gained nothing, and for that we will have to work. It's only beyond 2035 you will see that there will be lesser for non-fossil fuel based. So because of this use of significantly large amount of energy, fossil fuel based energy, you see the CO2 emission of India is like almost asymptotic to the y-axis over here. What it tells you is that India alone produces 3 billion tons of CO2 every year, and this is just CO2. If you see the other emissions which I don't want to talk about, which is also greenhouse gas emissions, These numbers are much larger. I am only talking about CO2 emission over here, and we produce 3 billion tons of CO2 every year, increasing at the rate of 5%. That basically mean if your interest rate is 5%, 6%, if you compound it, roughly in 10 years you will double. Okay. So by 2035, when we are talking about, we will be emitting roughly 6 billion tons of CO2 every year. It's a very challenging situation. Why? Because 11 billion tons is being emitted by China, 5.5 billion tons is being emitted by USA, and if you are emitting 6 billion tons, it basically means that you will be just next to China. Today we are third. Okay. So, and if you are the two largest economy who is emitting CO2, then entire onus would be on us to basically reduce the CO2 emission. Other countries will say, even today the in Azerbaijan, this last COP commit, they started saying, no, China and India, we should not consider it as developing country, we should consider them as developed country. As soon as they will be counting you as developed country, you will have to have 100% onus on reducing your CO2 emission. Right now, there is a lot of funds which you can basically utilize from World Bank and all other things. So, those challenges are there, let us not talk about that. Moving on. So, this is the story of green energy. I do not want to talk too much, but let me tell you there are other challenges over here, whether these are net zero processes or not, and if it is really net zero process, actually this is net zero for how long is what we have to also understand. So, this is the installation of solar. I know that we are increasing nicely, we have not reached our target, but that is not a problem. The problem starts later. See, when we talk about solar energy, it is an energy which has a plant load factor of roughly 20%. What exactly is plant load factor? Those people who are in industry would understand it better than the students. Plant load factor means that if I have installed capacity of 100 megawatt, how much I am actually producing from it. Okay. For example, if I in solar energy mostly, sunshine is only 6 hours a day maximum, okay, on average. We have to average over the entire year. So, summer time will have more sunshine, monsoon time like in Chennai from last 2-3 days we have not seen sun. Winter time in northern India will see no sun for many days. So, that basically mean on average you have sunshine for 6 hours a day. It basically mean you will have to install 5 times what you actually need. It basically mean that the plant load factor is 20%. Okay. If I am going to install 5 times, then only I will be able to have enough during the 6 hours of sunshine hour that I am going to utilize that electricity for the remaining 18 hours when I do not see sunshine. Okay. So, this is why the plant load factor of a solar energy is very poor. Now, the question is, if I am only producing electricity for the 6 hours a particular day, for the remaining 18 hours what do I do? Because electricity cannot be automatically stored, you need something to store it. So, now you have two options, majorly there are two options. Right now people talk about many other options, but let us say, let us be practical, two options. One of the option is batteries, where you will have to store this electricity for 18 hours at least, so that you will be able to use it for that remaining 18 hours. And the second option is hydrogen. Why hydrogen comes into picture? Hydrogen is not a fuel, they do not use it as a fuel, but I will give you the calculation of fuel. Hydrogen acts as a carrier means energy carrier. You have excess electricity during these 6 hours of sunshine times. One option is batteries, which I do not want to talk about, I am sure all of you understand it. Why hydrogen is a good example? Because hydrogen can be used for many in different ways. You can convert a hydrogen back into electricity, you can use hydrogen as a feedstock, you can use hydrogen for converting those carbon dioxide CCU, we talked about carbon dioxide utilization. If you are going to utilize carbon dioxide, how you will utilize it? You will have to mix it with hydrogen, there is no other way to utilize carbon dioxide. So, hydrogen you see comes everywhere, wherever you talk about whatever solution you need hydrogen. Okay, without hydrogen, and why do we need hydrogen? Because if you talk about human civilization, we have always only learned to use carbon and hydrogen, that is all. Our civilization is based on hydrocarbon. So, if you are not getting a hydrogen from fossil fuel, which is a typical source of hydrogen, then where you will get it from? You will have to basically split it from the water, there is no other way. Carbon you are talking about that we will get it from the atmosphere or wherever, but where the hydrogen will come from, you will have to split water. This is why hydrogen becomes a very essential discussion. You cannot get away, there is a lot of discussion, this country is going for battery, that country is going for hydrogen. Irrespective of which country you talk about, they will always have to produce hydrogen. Without hydrogen, they cannot really do anything if you talk about molecular level. So, let us look the story of the hydrogen, how does it look like? So, if I have to use hydrogen as an energy, what is the efficiency of this process. Okay. So currently you will have to split, you will have to use the electricity which you have basically produced during these 6 hours of sunshine to split water to produce hydrogen. You will split water, how much energy is required? 50 to 55 kilowatt hour. It basically means 50 units of electricity is required to produce 1 kg of hydrogen. If I am going to produce this electricity from solar panel, it makes sense. But if you are going to do the cost calculation, if you are going to produce this electricity from, say, the current electricity what we have, how much will be the cost minimum here? 500 rupees per kg, because 10 rupees, 9 rupees, 10 rupees is the cost of electricity. So 500 rupees per kg of hydrogen right away. It's not even green hydrogen, 100%. Okay. So the question here is, if I produce this hydrogen, the first question comes, who is going to buy it? Okay. If I am going to use 500 rupees per kg hydrogen in a process where I am saying that I will capture CO2 at what? From the atmosphere, if I capture CO2, how much it costs today? Roughly 300 rupees to 1000 rupees per kg. So if I am going to have two raw material which is going to cost me 500 rupees per kg, and I am going to add another raw material which costs me 500 rupees per kg. So the product which I am going to produce will become 200 rupees. Not possible, no? It will be beyond that. So the question is that if today I am getting 100 rupees liter, it pinches me. Tomorrow if someone will ask you up to pay 500 rupees for that same liter of gasoline or petrol, you will be happy with that? Not possible. So one has to always understand the economics when we talk about a solution. Okay. So this from financial angle does not look like looks a right solution, at least for countries like India, which is very price sensitive country. Most of the other Western countries are not that price sensitive. They don't mind. Okay, if you tell them that instead of $1 you have to pay $2, they don't even bother about it. Okay, we will do it in the name of sustainability. But here it's not about sustainability. Sustainability of human population is a big problem here. If your 90% of your population is not able to afford it, how you will make them sustainable? They will die without eating. So that is not sustainable. One has to always understand the sustainability aspect based on the society we are trying to solve a problem. Now let us not bother about the cost, let us look into the economics of the high CO2 footprint and all. So now this 1 kg of hydrogen which you have produced, you are going to produce hydrogen for what? For storing it for next 18 hours so that you can basically use it, or transport it somewhere else where the carbon dioxide is available so that you can utilize it. So even if you are going to store and transport for 100 meters or 500 meters, hydrogen being such a small molecule costs significantly large amount of energy, okay, compression cost and all. So 400 to 500 meter also, if you are going to transport and store hydrogen, it costs another 10 to 15 kilowatt hour of electricity. It basically means now 1 kg of hydrogen where it was produced and where it is being utilized has already consumed 65 kilowatt hour of electricity, 65 units of electricity. Now if I am going to convert it back into electricity, because I may need electricity, the 6 hours I have produced electricity, remaining 18 hours I am consuming electricity, my AC is running because of electricity. So I don't need hydrogen, I need to convert it back into electricity. So when I am converting it back into electricity with the best of the fuel cell which is available today, its fuel cell efficiency, I am not even talking about combustion, is even poor. So best of the fuel cell which is available today will only give you around 20 kilowatt hour of electricity. So you have consumed 65 and you are producing 20. So this is also a very poor in terms of plant load factor. I am not saying that you are not gaining anything, obviously you are gaining 20 kilowatt, no, that's not coming for free, but it's not zero CO2 footprint, please understand that. It's not, looks very glossy once we look at these numbers. The way in scientific literature you will see, oh, everything is, and the amount of electricity which we are going to need in India by 2050 is 5000 terawatt hour. What is our current installation? Much lower than that. This number 5000 terawatt hour I will show you. So now let's go deeper. Where the CO2 footprint challenge comes, we are talking about net zero CO2. Why we are talking about net zero CO2? We are saying that we will, once we move to green energy, we will be able to reduce our CO2 footprint. Currently our fossil fuel based economy has a significantly large CO2 footprint. Okay, let us try to look at the difference. You see, if I am going to produce 1 terawatt hour of electricity, if I am going to install a green plant, basically a fresh plant to produce 1 terawatt of electricity, if I am going to do it by coal, by natural gas, by biomass or by nuclear, I need to produce roughly 1000 ton of material. Okay. If I am producing 1000 ton of material, with that material I should be able to build a plant which will produce 1 terawatt hour of electricity. Okay. But if I have to produce 1 terawatt of electricity by green sources, renewable sources, I don't know how many of you took my thermo class, many of you were there. I always talk about quality of energy. See, the quality of energy when you talk about is very poor when we talk about renewable source, and if you try to compare, I will ask you to basically recall what we studied in Carnot efficiency. Carnot efficiency was the maximum efficiency which an engine can basically produce. If you look into that equation, efficiency was 1 minus T2 by T1. Okay, T2 was the sink temperature, T1 was the source temperature. So now if the source temperature is not very high, then this 1 minus T2 by T1 will not be closer to 1. Okay. So most of the renewable source of energy does not give you a source temperature which is very high, and this is why the quality of energy is very poor. Okay. So that basically means if I have to produce 1 terawatt hour of electricity by installing a new plant, that plant need to consume roughly 16,000 to 17,000 or 18,000 ton of material. Now this 18,000 tons of this material which you are going to produce today will not come from green sources. Okay, it typically comes from fossil fuel based product. What are these material we are talking about? We are talking about steel, we are talking about cement, we are talking about glass, we are talking about, and this is all there in the last slide. I don't want to go into much of detail. So these are there in the solar panel. So the point I am trying to make, if you now start looking into how much CO2 which you have already emitted. So these processes will emit CO2 while you are producing the electricity. This process will emit CO2 while you have you have put the plant itself. So there is the CO2 emission in the capital expenditure of this process, and this is during the operation of this particular process. Okay. Now let's look little deeper. Typically, when you are producing 1 kilogram of a material in a single step or dual step process, you would roughly produce 3 kilogram of CO2 if you are using fossil fuel to basically produce this material. For example, steel. On average, steel produces roughly 1 kg of steel will produce roughly 2.5 kilogram of CO2. Okay. So similarly, any other material which you are going to produce will have a CO2 footprint. If I am going to produce 16,000 tons of this material to produce 1 terawatt of electricity, I am already producing 48-50,000 tons of CO2. Okay. Now you will have to now understand that we are doing 5 times the required installation, because even though I need only X kilowatt hour of electricity, I will have to install 5 times of that because I need only 20% plant load factor is there. So now that 50,000 of CO2 footprint, 5 times of that becomes 250,000 of CO2 footprint. Okay. So what it basically means is that while this processes does not produce any CO2 while you are producing the electricity, these processes have a CO2 footprint which has to be divided over a period of the lifespan of the solar panel. Okay. Now if my lifespan of a solar panel is 20-25 years, a very good thing, because typically the number says that roughly around 5 years you should be able to get payback for the CO2 which has basically been produced during the installation phase, okay, from solar panel and all those things. So if I am going to produce electricity for 20 years from a solar panel, then that makes sense. I will go the remaining 15 years, first 5 years will basically balance out the CO2 footprint, but the remaining 15 years we will basically gain in that. But then look at from the other point which I was trying to discuss. When 2018 people predicted that, they said that by 2020 we will peak. Why they have not peaked? Because we are continuously installing new solar panels, new wind energy, all kind of things, even though we have sufficient capacity from fossil fuel. Okay, now when these new installations are coming, and as per this discussion, these new installations are actually adding the CO2 into the atmosphere, it is not reducing. So if these installations are not running for 5-10 years, it is not going to bring it down. So this is why this peak is not able to, you are not able to predict it, because you are not taking this into account that new installation which has to happen has already emitted the CO2 for next 10 years. Okay. So if something has already been emitted, otherwise this 10 years, this fossil fuel base would have slowly emitted those numbers. This you have already emitted at once. So more you do green right now, more CO2 will come into the atmosphere at this moment for the short period of time. Challenge will start when you start seeing the technology advancement will bring the challenge. 5 years down the line, a faculty will tell you, no, I have a solar panel which is 25% efficient. Today you are running a solar panel which is only 15% efficient. Change your solar panel. So 5 years down the line, you will be forced to change your solar panels. So when you are changing your solar panels 5 years down the line, what will happen to the CO2 footprint? Will we become net zero? Will not. This is the challenge. Okay, and this is bound to happen, because in 5, 6, 10, 7 years time, you will see that the efficiency of the solar panel, even the technologies will be changing. You will need new technology, more efficient and all. So you will again have to do the same thing. So it's a step where we cannot jump there, we cannot reach there that we will become net zero by so much time. It is a step change. It takes time to for doing all this. It does not happen automatically. So this was the story of green energy. I wanted to tell you, the take home message is, don't assume that a green energy is 100% net zero today. It's not. Okay. I gave an example of solar panel, but if you talk about any turbine or anything else, whenever we talk about turbines, for the blades which we talk about, you don't know how much material has gone into those blades, and those not a simple blades. They are designed material. When I talk about designed material, it basically means that these materials have gone through 5 different steps. Carbon fiber goes into it. Where you get the carbon fiber? Does it grow on tree that we will get and we will put it there? No, does not happen. This carbon fiber has gone through multiple steps, high temperature processes and all, has emitted huge amount of CO2 which we are not counting today. Okay. So each of these material which we talk about are the solutions which will make us net zero. I am not saying that they are not going to make us net zero. They will make you net zero, but it will take some time. Right now you are emitting all the CO2. So this is why this peak prediction actually is very difficult for us to do. So that green energy thing is done. Let's now look at CCUS, because this is another area and this is one focus of this particular presentation or this particular class. How much time do I have? Okay, no, I have enough time, don't worry. I would talk about the problems first, solutions we will talk about slowly. Solutions are difficult to come, easier to explain the problem. Okay, so now when we talk about carbon dioxide capture, utilization and sequestration, this is actually a 3-step process. Okay, CCUS, carbon dioxide capture, utilization and sequestration. What exactly it means is that first you will have to capture the carbon dioxide. Most of you are chemical engineer, it's basically separation process. We are separating carbon dioxide from other gases. Okay. What are these other gases? The other gases which comes out during the combustion of coal. Why we have to worry about it? Because coal is a solid. Okay. And you have to burn the coal with the gas. The other reactant is a gas. So when I have to react a solid with a gas, there is a problem. If you talk about a chemical engineering problem, there is a bigger problem, because solid has millions of molecules in this much space and a gas has few molecules in this much space. And if these two has to react together, the reaction has to happen 1:1. So if I have to make this true, that is, the reaction has to happen 1:1, I have to compress the gas, okay, and I will have to pulverize the coal. Both I will have to do. So this is why the combustion typically happens with excess supply of air. Okay, if it does not happen with excess supply of air, then instead of carbon dioxide you will produce carbon monoxide. You don't want that, because it will be a poisonous gas. CO2 at least is not a poisonous gas. It's loved by the plants. So you might die, but plants will survive. The human civilization will evolve again, which has happened multiple times. So it should not be a problem. You don't want carbon monoxide to come out from this process. So this is why it's typically done at a very high pressure or excess supply of air. Now why air? We could have done it with oxygen. No, it will produce only CO2 and little bit of additional oxygen. Would have been better? Maybe it would have been better, but then when these power plants were designed some 40-50 years back, they said, oh, there is only 20% oxygen in the air. If you have to separate oxygen from the air, it will be very expensive. Why do that? Let's burn it from the air itself. Okay. So 40 years back, we were worried about separating 20% oxygen from the air for combustion of coal. Today, we are ready to capture 400 ppm carbon dioxide from the atmosphere. So this is the story. What can you say? Okay. So this is the challenge. Air is what is now being used. So when you are using air, it has 80% roughly nitrogen, only 20% oxygen, and top of that you will have to have excess of air. So 80% becomes 85%, 90%. So by the time the combustion happens, you will see that there is only 10% carbon dioxide, 12% carbon dioxide, and remaining being nitrogen. So the CO2 capture process is basically a separation process, as a classical chemical engineering process of separating two molecules. Minimum two molecules will be there, one is CO2 and one is nitrogen. But in reality, you know, there are many molecules. CO2 is there, nitrogen is there, SOx is there, NOx is there, oxygen is there, all kind of crap is there which will actually kill you. But let's not worry about that. Right now, let's try to make it very simple. We have two molecules, carbon dioxide and nitrogen. Now the challenge is, there is a proverb, no? So if there is a rotten apple in a basket, every other apple gets rotten. So when there is a CO2 molecule in vicinity of one CO2 molecule in vicinity of 9 nitrogen molecule, this CO2 molecule will start behaving like nitrogen molecule. You know why? Because nitrogen molecule at room temperature has very high thermal energy. It's a small molecule. If you are giving little bit energy to it, it will jump like anything. Okay? If you are very light, you can jump. If you are heavy, you will not be able to jump. So it's a very small molecule. So at room temperature, it has a very high kinetic energy. And this kinetic energy, with that kinetic energy, it goes and bombards the CO2 molecule. So CO2 molecules also start jumping like nitrogen molecule. So now, what I was trying to do, I was trying to capture a CO2 molecule from this mixture. So if I have to capture someone and this guy is running, we need more people, not to capture it. This is the challenge. So when we talk about capturing CO2 from a flue gas, we have a point source is roughly 9 nitrogen molecule in one CO2 molecule. Now if I have to capture one person among 9 other person, it's not that difficult. Okay, I should be able to employ 5 people and they will run and they will catch that particular guy. But now the second problem is, what if we have to capture one among 2500? What is that problem? That is direct air capture. Okay, this is the elephant in the room. People talk about direct air capture is the future, because we have already produced all the carbon which we wanted to produce from under the ground. Now there is plenty of carbon above the ground. Why to unnecessarily dig under the ground for carbon? Let's capture all the carbon from the above the ground. We will convert it into chemical by adding hydrogen. This is what is CO2 utilization. This is what has been talked about. US is pumping billions of dollars. You know, they give $185 as subsidy if you are capturing 1 ton of carbon dioxide from air, directly from air. Okay, but look at the thermodynamics. We are talking about capturing one CO2 molecule from 2500 other molecule. How difficult that is going to be? You know, as a chemical engineer, it's going to be super difficult. Okay, it basically means that we need to understand that this process is lot more energy intensive compared to this process. There are certain advantages though over here. If you are directly capturing CO2 from the air, you don't have to worry about SOx, NOx and all other poisonous impurity which otherwise will poison your material. Okay, now coming to the material. If I have to capture someone, I need someone to capture it. No, I need a person. I will myself will go and have to hold some particular person. So when we say separating, it basically means we need a solvent, we need a material which will be used to separate. Okay. So the question here is, if I have to, what was the number for India? 3 billion tons. What was the number for world? 20 billion tons. So if I have to capture 20 billion tons of carbon dioxide, how much material I would need? Typically, even if you say that a material will be able to capture 10% of its weight, so we need 200 billion tons of this material. How much? 200 billion tons of this material. This is 20 billion tons every year. So it basically means I have to produce 200 billion tons of this material and recycle it for 20-30 times, so that for next 20-25 years I will be able to use this material to capture 20 billion tons every year? Is this not true? This is the challenge. If I am producing 200 billion tons of a material, how I am going to produce today? The same problem of solar panel. If I have to use cement and steel to place this solar panel, I am going to today, if I am producing, I am to produce with fossil fuel based energy. So if I am going to produce 200 billion tons of this material, how much more CO2 will get emitted? We will have to question that. So this is where the challenge is in net zero CO2. If I have to capture one molecule of CO2 from here, and by the time I put it back over here, in the entire process, the amount of CO2 which can come out should be less than one molecule. Is it possible otherwise? Otherwise you are not net zero, you are net positive. If you do nothing, you are producing 20 billion tons or 40 billion tons. If you do something, you are producing more than 40 billion tons. So are you net zero? This is the challenge. So the challenge here is that we have to understand that net zero is not about capture and utilization, sequestration, huge amount of gamma happens. Oh, I have identified a material which captures 1 gram more. Does not matter. You might capture 10 gram more, but you have to understand how much your material has already emitted the CO2. Okay, so you have captured the CO2. The question is whether one molecule of CO2 which you have captured is available over here by emitting less than one molecule of CO2. So the capture step should have at least 0.5, one molecule of CO2 I capture, and in the process I emit only 0.5 molecule of CO2, because this 0.5 molecule of CO2 is what I have saved in the capture process. I have another 2 steps to worry about. Okay. Now the second step is, if I am going to directly put it under the earth, I will have to transport and do all kind of energy equation, so that another 0.5 molecules of CO2 will get consumed. So one I have captured, one I have been able to do. This is possible if your scale of CO2 sequestration is huge. You can do this calculation to understand at what scale it will become CO2 neutral. Okay, this is possible. But when you talk about utilization, it's a very different ball game. So when we talk about utilization, where the challenge comes, hydrogen has to be produced now. Okay, so we looked into the number of CO2 footprint of hydrogen production, the solar panel and the splitting, the electrolyzer, the fuel cell, all kind of things. So basically hydrogen production should have lesser than 0.5 molecule of CO2 emission. Today the green hydrogen concept which we talk about in India basically means if 2 molecules of CO2 goes out, it will be considered as green. So if it's already 2 molecule, we are talking about 0.5, less than 0.5, how it will happen? Okay, so there is a challenge. So this is a challenge. Utilization will be contributing more CO2 and it will not be able to go to net zero. So these are some of the challenges. Cost obviously is one which I have stopped talking about. The cost here, for example, the direct point source capture is roughly $30 to $50 per ton, or in terms of Indian rupees, it turns out to be roughly 4 to 5 rupees per kg. Okay. You have some representative from Technip, they may claim that they have 3.5 rupees process, but I will tell you it's roughly 3.5, 4, 4.5, not less than that per kg. It comes out to be roughly $30 to $50 per ton from point source. Okay, and I am not even talking about many other processes which we will see later. If I am going to capture this from here, the subsidy given is $185. So you can imagine what will be the actual cost. Okay, so that's. Now if I have to, in India, if I have to capture 1 billion ton, multiply it by $50, how much money will get consumed? But at the end of the day, I am trying to say that all this is possible if we basically be aware what we have to achieve. We should be able to achieve it if we know what we have to basically design it for. Okay, the designing has to be done for net zero, nothing else. If we are not designing it for net zero, it will not become net zero. All this I have already discussed, I will quickly move on. This is the material. For example, you will have some geolite, some metal organic framework. Typical number is 0.1 to 1 gram of CO2 per gram of XXS. So if I have to capture 2.9 billion tons of CO2, I need 2.9 billion kilogram of MOF, and regenerate is 100 to 1000 times. All this I have already talked about. You don't even know how to generate an MOF, for example, or any other exotic material, for example. You know, in labs, it takes 1 day, 2 days to produce 1 gram. Okay, I am not talking about the time here. I am talking about if you are running it for 1 or 2 days by using the same energy which comes from fossil fuel. Look at the CO2 footprint of this material. Okay, this material have not 3 kilogram of CO2 footprint, they have 10 kilogram of CO2 footprint. And this is the same story for all those carbon fiber reinforced wind turbine and all those things. Okay, these challenges are there. Industry say that we have monoethanolamine, diethanolamine and all those things, and technique, the solution they might tell you is that amine based solution. We also talk about it, we also do similar research. But let us look at the challenge over here. This is the molecule which is supposed to be the God molecule in this particular case, which will capture all our CO2 and will get rid of all our problem. But where this molecule comes from? Does it come from air? Does not. We will have to produce this molecule. How we will produce this molecule? We have to produce this molecule by reacting ammonia and ethylene oxide. Okay. The ammonia which currently produces monoethanolamine, is it green ammonia? Not green ammonia. It is grey ammonia, black ammonia, and you know ammonia process is 300 bar 300 degree centigrade. Can it be done without CO2 emission? So first this monoethanolamine has to capture the CO2 coming out from this ammonia processing, and then it has to do from the ethylene oxide processing, and then if this is still around, then it will capture the CO2 from here. That means in doing this, if it gets consumed, then this CO2 will remain like that. Okay. So this is a challenge. This is a challenge. The other challenge is that ethylene oxide, for example, the only source of ethylene oxide today is what? A fossil fuel. Do you have any other source of producing ethylene oxide today? No. Everything comes from a fossil fuel. The only other way of producing it is planting trees. That is a very unique story. Today I do not have time to talk about, so we will skip that. Okay. I have another 5 minutes, I will try to finish it off in 5-6 minutes. This is the largest direct air capture plant, which is called Orca, is in Iceland. Okay, beautiful plant, excellent technology. Okay, how much it captures? It captures 4,000 tons of CO2 every year. Tell me how much tons of cement and steel has gone into production of this plant. This plant has already emitted 10 years of CO2, what it can capture, maybe more. Is it net zero? Maybe if it runs for 50 years. But do you think it will run for 50 years? The technologies which are being used, Gen 1, Gen 0 technology, what we will call it, do you think it will be running for 50 years? I doubt. Maybe we can change the material, the construction will there, but if it is corrosive material, will it, I know, I will tell you, oil and gas, many of you are from, these amine based processes which actually being utilized to capture CO2 from natural gas and all, hardly 5-6 years is the lifetime, they change it. They make lot of money, so they change it, they do not bother. Here you do not make lot of money, these are all money consumer, so you will not be able, so these are the challenges. Okay. Forget about the remaining slides. So we do all that in our group over here, so don't want to do a marketing in this particular class. Let's move on. Okay. So when we talk about CO2 capture, we know now that we have to generate a material to capture CO2. Okay. What if we don't generate a material to capture CO2? Because if you are generating a material, 1 kg of MO, if you want to generate, you will produce 10 kilogram of CO2. Your net zero becomes not a possible solution. But if I do not generate a material, I take a material which already exists, then I do not emit that 10 molecules of CO2 for that 1 kilogram of material which or 1 molecule of material which I have just used. Okay. So there are different solutions, different composition of CO2, oxygen, nitrogen, hydrogen, H2O, CH4. In each of these I do not want to go in there. So depending upon the concentration of CO2, you have different solutions. One of the best way of capturing CO2 is not going for a chemical route, but going for a physical route. What is physical route and what is chemical route? Chemical route basically mean that the CO2 is going to chemically react with the material with, in which it has to be captured. Okay. So if I have a mixture of CO2 and nitrogen, I have two options. I expose this gas mixture to a material which chemically reacts with CO2. Okay. So this is called chemical route. Why we need this material? We need this material because the binding chemical energy is much stronger. So even if my concentration of CO2 is low in my feed gas, if I am using a chemical, it will be able to react really fast. Okay, why fast is important? Because we are talking about tons and tons of this material. You need a kinetics which is like really fast. Otherwise your CO2 molecule will run away, you will not be able to capture it, you will have to capture it really fast. So you need a material which has very fast kinetics. And which material will have very fast kinetics? If it is thermodynamically very much feasible for it at that temperature and pressure condition, so a chemical reactant will be able to achieve this much easily compared to a physical adsorbent, which actually how it separates, it dissolves it in a larger quantity compared to nitrogen, or it absorbs it in a larger quantity compared to nitrogen. So when we talk about a physical approach, it's not molecular recognition which is there, it's there to certain extent, but it's not 100% molecular recognition. When we talk about chemicals, it recognizes the molecule and it captures it. It will not capture even a single nitrogen molecule, because that recognition ability in a chemical is much better compared to a physical material. Okay, a physical material will capture based on van der Waals interaction. Okay, so van der Waals interaction will be there in every molecule, whether it is a small molecule like nitrogen or large molecule like CO2. Both of them will have van der Waals interaction. CO2 will have higher van der Waals interaction, so it will be able to capture faster compared to nitrogen, which is slightly slower. So in this process, physical process is more about enrichment. It's not about complete separation. Okay, so typically if you are looking for 100% separation, you will have to go for chemical approach. If you are looking for separating CO2 from a gas stream which is very lean in carbon dioxide, you will have to go to chemical approach. But if you are looking for gas mixture, if you are looking to capture CO2 from a mixture which has more CO2 compared to nitrogen or compared to the other gas, you will be able to use a physical approach. The advantage of physical approach is, physical approach basically allows you to regenerate your material multiple times. When there is a reaction between A and B will react to produce C. Okay, unfortunately when the reaction happens at the temperature of our interest and during a regeneration, A and B reacts to produce C, but also C square gets formed, BC get forms, AC get formed, all kind of product gets formed. You cannot control, little bit will form, but it will form. This little bit formation of this material basically results in poor regeneration of the material. So we talked about huge amount of material required for capturing CO2, and what is the essential component there? Regeneration. If I am not able to regenerate, then the entire process is gone down the drain. So regenerability is a big thing. In chemical processes, regenerability becomes a question mark. 100% of material you will not be able to regenerate. Every time you regenerate, some material will be lost. The same thing is not true for physical process, because there is no chemical reaction between them. They are just coming close to each other. And this example I give many times in my class, it's more of having a boyfriend and a girlfriend, you can always break. And typically the human Indian social system, it's chemical reaction is more of a marriage. You will have to divorce. There is a big threshold for that. Okay, so this is the difference between a physical material and a chemical, where this is difficult for you to basically separate it out. This results into a CO2 capture process, basically mean it's a capture and regeneration both built together. So if you are talking about a chemical process which will have low capture cost but high regeneration cost, because if you really like these two molecules, if really like each other, I will have to really pull them apart with lot of energy to separate them. But if these two molecules don't like each other that strongly, then with lesser force I will be able to pull them apart. So when we talk about CO2 capture, it's inherently two-step process. Capture itself is first capture and the second regeneration. So in chemical process, capture cost is less, regeneration cost is high. In physical approach, capture cost is high because you need to pressurize, you will have to bring them together, you will have to push them very close to each other by pressurizing, by bringing them at lower temperature. That will take you a lot more energy. But when you have to separate them apart, it will automatically happen, or lesser amount of energy will get consumed. So when we talk about a capture cost, both of has to be calculated together. The capture as well as regeneration of chemical process, capture as well as regeneration for physical process, and then only you can compare which will be better suitable in terms of total CO2 footprint or total energy. One such process which we have worked on is gas hydrate. This is, I am giving only 2-3 minutes for this process. I don't have time. I have given you the story. I will give you few solutions. Gas hydrate is one such process where you do not need to generate a new material. I am using water, not fresh water. I can use sewage water, I can use effluent water, I can use sea water, I can use any water, does not matter. I will be able to bring this water and this gas mixture together, and this would convert into this kind of hydrate. Once this converts into this kind of hydrate, I have achieved 2-3 things. Where the advantage comes from this process, I will tell you. 3 things I have achieved. 1, I have purified the water, because once hydrate will form, it will only form with the pure water molecule. Okay. So, all the water molecule will come together and form this ice like crystals. So, if I separate out this crystal, I have got pure water if I dissociate it. Okay. One thing I have done there. The second thing which I have done, when I have huge amount of solar energy available for the 6 hours period, I can form huge amount of hydrate during these 6 hours of period. Large amount of hydrate I will form. What I have done? I have stored all those energy in the form of the enthalpy of hydrate formation. Okay, because when I will have no sunshine, when I will dissociate this hydrate, it's an endothermic process. So my temperature will keep going down, so I will be able to do my cooling, all kind of things which require 60% of energy from a building. I will be able to do all of that. Second, in this, so what I did first, I separated pure water from a contaminated water. Second, I have stored huge amount of sun energy, which anyway I wanted batteries or something else to be somewhere is to be stored, so I have stored it already in the form of hydrate. And the third is the separation of gas, which was our main goal. Okay. So that's all for from me today. We will not talk too much about all of these. There are a lot of fundamentals on hydrate. Do you have? Should we go for another 5 minutes, Jitendra, if you allow, maybe? Okay, fine. So if you talk about hydrates, let me quickly go back into little bit of molecular level over here. When we talk about hydrates and separating a gas mixture by hydrate formation, you see hydrates forms typically in these 3 structure in the lab. Okay, when I say in the lab, because this is what you can relatively in lab, many other structures form, but typically at moderate temperature and pressure. Structure 1, structure 2 and structure H. Let us not bother about the structure. What we should understand here is that all the 3 types of a structure has different size of cages in it. Okay. So if I have a mixture of carbon dioxide and nitrogen, okay, and if it forms a structure 1 hydrate, now let me tell you, the CO2 will easily go into the large cage as well as nitrogen will go into the large cage. But nitrogen is a small molecule, cage is large. So if I am putting nitrogen in a small cage, it's a free movement for nitrogen. I'll have to really pressurize it too much for it to remain in that particular cage. If I am not going to high pressure, the nitrogen would go in, will come out. It will not really get stored in there. The same thing cannot be said for CO2. At a moderate pressure also, CO2 will go into the cage and will sit in there. Okay, because the size is bigger. It will, because of the pressure. See, the chemical potential difference is there. If I have a cage, there are 2 ways by which we can understand it. If I have a cage which is empty, and if I have all the CO2 which is outside, so what is the chemical potential difference tells you? That if there is too much of CO2 molecule on the outside of this particular cage, this CO2 molecule will look around and say, oh, this is where I don't have any CO2 molecule. This is one real space I can occupy. So it's a problem of real estate. It's too crowded, too expensive. Let's move into this place where there is no one. I will go and occupy that. So that chemical potential difference allows the CO2 to go into that location. But once it goes in there, it gets trapped. On the other hand, when nitrogen goes in there, it's too big for it, so it comes out. Okay. So now if I have to capture CO2 and nitrogen, CO2 from CO2 and nitrogen mixture, you will have to understand that CO2 will typically go into the large cage and nitrogen will typically go into the small cage. Okay. It will mostly like to sit into the small cage. Large cage also there will be, as I was telling you, it's not 100% separation. Always physical process will be enrichment of one. So what I have to do in this? If I somehow block the small cages over here, nitrogen will not be able to go in there. How do I do it is our challenge. Okay, this is where we have to work on. How do I block the small cages so that nothing goes in there? If I can somehow put a molecule, now there is a chemical engineering problem. What we are trying to do? We have a liquid water, we are trying to push gas into it. But if I put some other liquid molecule which is small enough but is still in liquid phase and will block the small cages, then this mass transfer limitation is not a problem for me, or it will become so much a problem that nitrogen will not get the time to go in there. So all these you will have to basically utilize in this particular case. Similarly, when I am going to form a structure 2 hydrate, there is lot many more small cages compared to large cages in a structure 2 hydrate. So, if I have to separate CO2 and nitrogen, I should primarily go for structure 1 because there is lot many more large cages. I will be able to enrich it with CO2. Okay. If I am forming a structure 2 hydrate, then it's a challenge, because now when I am forming a structure 2 hydrate, what we are doing typically, we block the large cages. How do we block the large cages? We block the large cages by adding another molecule like THF or some type other cyclopentane, whatever we put in there. Once we put in there, these 8 cages are not available for CO2 or nitrogen. Then this cage is available for either CO2 or nitrogen. But here the problem is the CO2 is slightly too big for small cages. Okay, this is why our separation efficiency goes down. But still, what has been seen is that the small cage in structure 2 actually is more attractive to CO2 compared to a small cage in structure 1, because if CO2 is able to go to the large cages, they are not going to the small cages there. But in this particular case, since all the large cages are packed, CO2 likes to go into the small cages now. So now those who are not in hydrate, they will find all this boring, but those who are in hydrates, we can have a separate discussion on some of these things. Okay. Similarly, we can separate between CO2 and methane and all, what exactly is required, all those things has to be step by step has to be thought, then everything can be designed. So the other thing which we typically design in hydrate process is two things we design. One is a classical chemical engineering process where there is multi-phase, multi-component system. So when you talk about a multi-phase, multi-component system, then mass transfer and heat transfer becomes a big challenge. Okay. Why mass transfer? Because a gas has to diffuse through the liquid. Okay. Now there is another information which I will give you, and I will try to stop in another couple of minutes. Water being 18 molecular weight should not be in liquid phase. It's in liquid phase because of the hydrogen bonding. So if I have to enhance the diffusion of gas in liquid water, one best option for me is to weaken the hydrogen bonding between the water molecule, so that other gases will be able to diffuse faster. And this is what is basically being done by using some surfactant. Little bit amount of surfactant is added into the water, so that the hydrogen bonding strength goes down, the viscosity goes down, and it will be easier for the CO2 or other gases to diffuse into this. But the same thing will not work when you are going to use THF, because THF will dictate everything. So all those challenges are there. Moving on, too much of details. So we have developed some of the processes of CO2 capture. We are trying to do a scale up of this. This only works when you have roughly 25 to 30% CO2, remaining nitrogen and hydrogen. If you have only 10% CO2, this is a very expensive process. You will not be able to basically achieve the same amount of input from there. That's all we have. We can talk about CO2 sequestration and all, but not for today maybe. So some of the other demonstration units which we have had in our lab, again no need to do any advertisement among the students. These are basically there to get money from industry, those guys.